In this video, we'll solve our first quantum mechanical problem, the one-dimensional infinite square well. We'll start by defining the potential, getting the general solution, applying the boundary conditions, and finally normalizing the solution and calculating the energies. The infinite square well is a potential that is zero inside the well, which is goes from x equals 0 to a, and it's infinite otherwise. If we draw it with hard walls where the wave function is confined to this region of space, which is from 0 to a, and the walls are infinitely hard. Outside the well, the solution must be equal to 0, and inside the well, the Schrodinger equation has no potential, and so it's very simple. It's minus h bar squared over 2m, the second derivative of psi with respect to x squared, equals E times psi. If we rearrange this by just pulling the derivatives, second derivative of psi on one side, we get second derivative of psi with respect to x is equal to minus 2me over h bar squared times psi. Now these are all positive constants, and so we can substitute this with the value k, which is equal to square root of 2me over h bar, so this becomes k squared. And then we have minus k squared times psi is equal to second derivative of psi with respect to x squared. Now, this is a classical standing wave boundary value problem, and we know what the general solution looks like. It is a sine and a cosine. These are the functions that when you take the second derivative, you get the same function back again with a negative constant in front. And so the solution we have is psi of x is equal to a sine of kx plus b cosine of kx. So if we take the second derivative of this first term, we'll get sine back again, but we'll get minus k squared out. The same thing with the b, with the cosine part, we take the second derivative, we'll get minus k squared times the function back again. So this is our solution. And we're going to apply the boundary conditions. And the boundary conditions are that at 0 and at a, the wave function must go to 0. Not only that, but the derivative must be 0 as well. And it must be because it's going to be 0 beyond that. So there's a discontinuity in the derivative at that point. And this means it's not a physical function, as we'll find out later. But that's okay because it can be used as a reasonable approximation for many physical systems. So for psi is equal to 0, at 0, we just plug this into the Schrodinger equation. We get 0 is equal to a sine 0 plus b cosine 0, but the sine of 0 is just 0. So this term goes away. And we're left that b cosine 0, which is 1, is equal to 0, and consequently, we find out that b, the coefficient of the cosine, is equal to 0. That is, there is no cosine component. If we now apply the same boundary condition to the right, that is on the x equals a side, we have for psi of a is equal to 0, we have 0 is equal to a times the sine of ka plus b times the cosine of ka. Now b is 0, so this thing goes away. And we're left with 0 is equal to a times the sine of k lowercase a. But we know how to do that because sine goes to 0 periodically whenever this argument is a multiple of pi. And so if we start at 0, we've already taken into account, but we can rewrite this as that Ka must be equal to n pi, where n is an integer. Under those conditions, this equation will be fulfilled. This means that K is equal to n pi over a, where n is equal to 1, 2, 3, and so on. It goes on to infinity because these hard walls go up to infinity. What this means is that we've quantized this value k. That is, k can only hold values that are integer multiples of pi over a. So the wave function turns out to be then psi sub n of x is equal to a times the sine of n pi over a x. And the energy of this nth state is going to be the expectation value of the Hamiltonian. where now we've defined this bra n and ket n as psi sub n, or the nth wave function. It's even more of a shorthand. So all that remains now to solve the problem is to calculate E sub n and normalize psi of n. And we're going to do that next. So we'll start first with the normalization. The normalization integral in bracket notation is just 1 is equal to the inner product, this bracket of n and n. So it's the same function on both sides. Well, I can expand that back to the integral, which is the integral from 0 to a of modulus of a squared. Remember we have to calculate this now. That's what we're calculating. Sine squared k sub n x dx, where k sub n is n pi over a. But that's not important for this particular moment. So when we integrate sine squared, this is a constant that comes out. We integrate sine squared, we know that for an integer number of half wavelengths, or half periods of the sine function, the integral of sine squared is 1/2 times the distance over which you integrate. And so this just becomes a over 2. So we get capital A modulus squared times a over 2 is equal to 1. And this means we can solve for a. Capital A is just the square root of 2 over lowercase a. And note that this doesn't depend on n. It's the same for all functions. And so my final nth wave function is equal to psi sub n of x is equal to square root of 2 over a sine of n pi over a x. Now we want to calculate the energy. So the energy of the nth state is calculated by first applying the Hamiltonian to that wave function. And that's easy enough because the Hamiltonian is just the second derivative times minus h bar squared over 2m. So we have minus h bar squared over 2m d squared by dx squared of a sine n pi over ax. When I take the second derivative of a sinusoid, I pull out this constant with a minus sign, this constant squared with a minus sign, and then I keep the structure the same. That minus sign will cancel this minus sign, and so we get plus n squared pi squared h bar squared over 2m a squared, and my function back again. When I then close the, I can look at this. This is basically the nth function, which I can represent with a ket. So when I do the expectation value, I have to close it on the left side with a bra and do the integral. And so schematically, that looks like this. E sub n is equal to bra n and then h applied to n. But we know what h applied to n is. It just gives me n back with a constant in front. I pull the constant out. I get n squared pi squared h bar squared over 2m a squared. And then I have n bracket n. And that is simply my normalization integral. That must be 1 because we've normalized the functions. So this just gives me 1. This means the energy is n squared pi squared h bar squared over 2m a squared. So that's the energy of the nth state. Now what do these states look like? And we can rewrite this as h bar squared k sub n squared over 2m, where k sub n is the wave number of the wave function. So if we look at the first 3 states, you can clearly see what the trends are. You start with the n equals 1 state. That's just a half wavelength of sine. The n equals 2 is a full wavelength of the sine function. N equals 3 is 1.5 wavelengths. So n is equal to 1 has no zeros inside. It's only zeros at the edges. N equals 2 has 1 0. N equals 2 has 2 zeros. And so the number of zeros is just n minus 1.